Okay. So yeah. So in this question, what they are asking is, suppose the input layer of a fully connected neural network has four nodes. So the input is having four nodes. The value of a node in the first hidden layer after applying sigmoid non-linearity is V. So you applied sigmoid function and it's saying for value the first hidden layer node. So there is a hidden layer node and the output of this is V. Value before applying sigmoid, sorry. So whatever you are getting here. So there are two halves. One will be summation Wixi and the output of this will be sigmoid Wixi summation. So this part is V. Value of a node in the first hidden layer before applying sigmoid nonlinearity is V. V is equal to this summation that is input to this first hidden layer node. Now each of the input layers nodes are scaled up by 8 times. Okay. So instead of this, what is happening is each input is now 8 times x1, 8 times x2, 8 times x3, 8 times x4, and you have the hidden layer node. So what will be the value of the neuron with the updated input layer? So when we are linearly multiplying something and then we are doing a weighted addition, so that 8 will come out, right? It will become 8 times summation wi xi because 8 is multiplied to each of the xi. So this is 8 times v. So then that value of that neuron is 8v. So any linear scaling would have resulted in this in that thing only. If I multiplied it by k, then I would get k times v. So the sigma value will increase by doing the scaling because sigmoid function is monotonic. That means if I increase x, then sigma x also increases. Okay. So if there's any doubt, then just let me know. Which of the following properties, if present in an activation function, cannot be used in a neural network? The function is periodic, the function is monotonic, the function is unbounded. The function is periodic. So one periodic function is like sin x or cos x. This is a periodic function. And what happens in sin x cos x is you have something like this, right? Oh, sorry. It is like this. So this is sin x. So what is happening in different values of x, like you will have the same sin x value. So it doesn't differentiate, like the essentially your you only get this much range in your for your input variable, because whatever else value you give, it will everything will be mapped to this -1 to 1 range only. and many values will map to 1. Like many values will be mapped to this point. Gradient at this point is 0. It need not be that for all periodic functions you have something like gradient 0, but it is possible. And this can also be a periodic function. But here the gradient is not 0, but at this point the gradient is not really defined. But what is happening is the same x is like the same f of x is mapped to different x values. So the function is periodic is not a property that we want. So this is one of the properties. The other property is function is monotonic. So your ReLU function, which is something like this, that is monotonic, or even your sigmoid function, which is something like this, between 1 and 0. Sigma equals to 1 upon 1 plus e power minus x, right? So this is also monotonic function sigmoid. The function is unbounded. So this ReLU function is unbounded above. The ReLU range is between 0 to infinity, right? So it is unbounded above. So these properties are fine. So we can say A is the property which cannot be used in a neural network. That the function is periodic. I mean, I'm not able to think of any utility where, in a practical sense, where you may want it. But there may be some application which, at some point, it may be useful to someone. But right now, in our current study and in the popular use cases, this periodicity is not really desirable. Okay. Any doubts? Okay. What is the main benefit of stacking multiple layers of neurons with nonlinear activation functions over a single layer perceptron? What is the benefit? He is saying it reduces complexity of the network. So in a sense, it increases the complexity of the network when you have many, when you have many layers. Like I think this was given in that also. F2, F3. Similarly, you have some Fn. If you have n layers, so your output O is actually a function of Fn is a function of Fn minus 1, Fn minus 2 till f1 of x, and similarly n brackets will come here. So it's a very complex function. When you are having many layers, you're getting a very complex function. reduces inference time during testing. So when you have many layers, you have to do all the computations. You have to do first this computation has to be done. So all the computation in this layer, they can be done parallelly. But from this computation can the next layer F2 computation can only be done after F1 computations have been done. So the more layers, like Fn has to wait for F1, F2, F3, F4, all of them to compute till that till Fn gets an input. So the testing time is actually the inference time is increased during testing. It's not decreased. Allows to create nonlinear decision boundaries. So this is true because in the single layer perceptron you don't have like any like activation function, like a nonlinear activation function which is creating a nonlinear decision boundary. Single layer perceptron creates a linear decision boundary, while having a single hidden layer itself creates a nonlinear decision boundary, and having multiple of these increases the complexity of these decision boundaries. So C is the correct answer. It allows to create nonlinear decision boundaries. Any doubts? Okay. Which activation function is not analytically differentiable for all real values of the given input? The activation function that is not analytical. So it is asking which activation function is not analytically differentiable. So sigmoid is what? 1 upon 1 plus e power minus x 0 1. So sigmoid is something like this, right? This is like smooth go through 0.5. And this is sigmoid. So by looking at the graph, you can say like it is differentiable at all points. The gradient is the tangent. Okay. In tan h also, it's similar to sigmoid, just the range changes. Tan h e power x plus e power x minus e power minus x upon e power x plus e power minus x. I think this we can just verify if this is correct. So you have 1, it's a minus 1 here, and your function is something like this. Okay, this is also differentiable at all points. So in the ReLU function, it is not differentiable. So your ReLU function is like this and like this. ReLU is max of ReLU of x is equal to max 0 comma x. So when x is negative, it takes 0, and x is positive, it takes whatever the x value is. So at this point, it is not really differentiable because the gradient is along this or along this. It is not very clear. So you take either of one of these. That is usually what you do. You either consider it 0 or you consider it 1. Usually it's considered 0. Okay. Any doubts? So C is the answer. So all these different activation functions, like, they can have, depending on what kind of input you are working with, and what kind of training you are doing, what kind of loss functions you are using, what you want to use may vary. Like currently, many of the networks ReLU is popular because some properties have been observed in theory, which favors it, and in practice also. Like vanishing gradient, which was discussed in the class, I think. That does not happen with ReLU. It happens with sigmoid. Maybe I'll just discuss that after I have solved all the questions. So they're saying consider an MLP with D nodes in input layer, M nodes in the hidden layer, and K nodes in the output layer. All nodes use sigmoidal activation function. So you have there are D nodes here, M nodes, and K nodes in output. Some connections are there. And all nodes use sigmoidal activation function. How many weights and biases does the network have? So if you look at this part, here there are D inputs, and if you consider one of the node here, then it has D connections coming to it. This node H1, hidden layer first node, H1 has D connections to it, so it will have corresponding W I, or I can say WI1, where I is from 1 to D. Similarly, Wij, so if this is for first hidden layer, I can say W1 hidden layer 1, Wi1 is the weights coming to hidden layer first node, Wij superscript 1. Here j will vary from 1 to m for each node in the hidden layer, and I is from 1 to d for each node in the input layer. So what you have is basically d into m weights, right? Because this Wij will form a d cross m matrix. And if each node has a bias, then you will have m biases. Similarly, from here to here, you will have mk plus k biases. So dm plus mk is the number of weights, and m plus k number of weights, and m plus k is the number of biases. So like for h1 computation you have sigma of summation w1 I1 xi, I is equal to 1 to d plus b1 say. This is the bias, I can say superscript 1 bias for uh, first hidden layer, first node for some h uh, L or something. It will be sigma summation I equal to 1 to d w il first hidden layer xi plus bl1. Okay. Now they are asking, so we know what is the answer for first option. It is this, the first question. Number of bias equal to 2. So each node in the hidden layer will have a bias, right? So if you see, if you have d inputs, and this bias is like this plus 1 value, and you have m nodes, so here this b1 will be there, b2 like that, b3, this weight will be there from plus 1, and this will have again inputs. This is your d-dimensional input. This is the bias node, and the bias node is connected to each node in the hidden layer. Similarly here also there will be one plus 1, and this plus 1 will be connected to each node in the output layer, k nodes. So it is connected to each of them, so there will be one bias weight b21, b22, b2k, here will be b2m, b1m, b12 for first layer, first all the first layer biases, all the second layer biases. Okay. So how many computation is needed for one forward pass? One forward pass means one input you are passing, or one batch you are passing through the network. So you can just consider one input. If you are passing one input, then in the first layer there is no computation being done. It's just the input is taken here. Here, in the first part there is a summation done. Actually, first there is a multiplication done, w1 into xi, wi1 into xi. So like for the first hidden layer there are d multiplications done. So if you consider multiplications, number of multiplications, so in h1, let us copy, sorry, So in H1, if you see, there are d multiplications done. D multiplications done, and it will be done for each hidden layer. So d into m. Similarly, in the output layer also there will be m multiplications done for each of the output nodes. So it will be d into m plus m into k. So we have counted all the multiplications. Now how many additions are done? Number of additions. Additions are, here there are d additions done plus 1, right? So d plus 1 additions, and that will be done for each node. D plus 1 into m. Similarly, m plus 1 into k. And number of activations. So in the hidden layer, there are m nodes. So m activations in the hidden layer, and k activations in the output layer. In the input layer, there are no activations. So m plus k activations. So these, you can say, are the total number of operations, computation that is needed in one forward pass. So in practice, when you do these things on the GPU, usually neural networks are trained on graphic processes, because graphic processes have this history of being used for graphics, basically for a display, and they are designed in such way that, so if your screen is basically a matrix of pixels, and when the pixels are changing, these matrix operations are like in like VFX and everything. They're basically graphics operations happening in gaming and all. You have these animations and stuff. They are happening via matrix operations. So on this display, on your display matrix, like 1024 cross 1024, whatever display resolution you have, on that matrix, operations are happening. And usually there will be some RGB or something like that. 3 layers of that matrix, just to give an example. So the graphic is designed to do operations parallelly on big matrices, and your CPU cannot do a large number of operations parallelly. It can do like, there will be like octa-core, your CPU might be 8 core, something like that, 16 core. So if 16 core, you can multi-thread it to 32 threads, and you can do 32 sort of parallel operations. But these GPUs have thousands of cores, and on each core, an operation is done parallelly. So this neural network training happens in usually GPUs, and these operations will be done, like each layer operation will be done. Each of this, like this to this, all will be like all hidden layer operations. They will be computed at the same time on the graphic processor. So that's how usually the implementation wise how it happens. Okay. So we found out all this, how many operations are there. So any doubts? Okay. So in this question it is asked, how does gradient descent update the neural network weights? So here how they are updating this, wi is equal to wi plus eta times summation of xj. So you can say xj is the input, wi is uh, let's say weight of some node I in some intermediate layer. Eta is learning rate. So here I don't know, this can, here there is an addition. This is possible only if, like here they are saying it is gradient descent update. So in your neural network, we learnt about loss functions like squared loss, cross entropy loss. So if j was your loss function, let me take L. So here here this j is given, so that may be the loss function. So if j was some form, that if I take the partial derivative del j by del w, which is equal to minus of xj summation, then my weight update would be minus eta del jy del wi, and this is summation minus xi, but we are not given any information about what is my loss function or cost function, so we can say this is wrong. Similarly this also we can say is wrong. Here we are given like this is your cost function in terms of the current whatever parameter wr, and you are taking the partial derivative with respect to wi, the weight which you want to update, and you are doing a descent step. So if your cost function, if this is your wi, this is your cost function, and it is varying something like this. So if you are here in wi, your partial derivative will give you the slope of this del j del wi will give the slope, and you want to take a step in the negative direction of this. You want to take a step in this direction, the negative of the gradient. So from wi value from here, you will take learning rate times some here. If this was your wi, you move your wi to this value here. Okay, so that is what this is doing, and that option is given here. You don't want to add, you don't want to go in this direction where the gradient is actually increasing, so your cost function is increasing, but you want to minimize the cost, you want to minimize the loss. That is what you try to do in training your neural network, whether it be cross entropy loss or squared error loss or any other appropriate loss. Okay, any doubts so far? Okay, So here they are asking, consider the following feed forward network. All weights and biases are as shown in this figure. All nodes except the input nodes use sigmoidal activation function. Suppose the input is given 1 point, this is 1.0, 0.5, and the desired output, whatever your target, is 0.5, 0.5. Suppose we are using squared error loss. Find the weight update using back equation for the weight shown in by a thick arrow in this figure. So I have drawn this figure, and they are asking to find the weight update for this. So what is the first step that we need to do? So our output is whatever a cost function. If you try to see, it is squared error half uh, oj minus tj summation j squared, right? But we are asked the weight update for this layer. So I can say that particular is W1 for first hidden layer, uh, 1 1 from first node to first hidden layer input. So I have to compute the partial derivative W1 1 1. So I think this was derived also in the class. So if I say OJ is the output of this layer, O2, O1, and this is X1. So what I will want is, because OJ is a function of the previous things, del J by del W1 is del J by OJ2 into summation J del J by del OJ2 into del OJ2 by del W11, right? And del OJ2 by del W111 is equal to, now each OJ is input from the previous layer, this thing. So del OJ, and let's say 2 by del OJ1 into So I think I should take here some other. I need only this one. So I'll take O1 1 and here del O1 1 by del W1 1. Okay. This is what we want to compute. For that we need this, and for this term we need this. So I'll try to increase the page size. So del j by del oj2. So oj is your output from here, o2j, and from here whatever is there it is o1j. O2 subscript 1 will be for the first, O2 subscript 2 will be for the second, like that. So this what you get is, so this 2 is not square, so just remember that. But what you will get is oj minus tj. Yeah, this is what you will get, 2j minus tj. Sorry, oj minus tj. This is del j by del 2 oj, and for computing this term you need this. So they are saying it is sigmoid activation function, right? So when I am computing del oj2 by del o1 1, just interrupt me if you have any doubt or if I made some mistake, if you feel I made some mistake. So your o2j is what? It is sigma summation of o1i into wi plus some b. So you are taking derivative of this. So when you apply chain rule, uh, derivative of sigma x is, I think, sigma x into 1 minus sigma x, right? This is the partial derivative of sigmoid function. So we have this summation. So this will be summation I o1i wi plus b into, oh no, sorry. So sigma of this is O2j only, na? So this is, so what I wanted to write was partial derivative of O2j by W, sorry, OI O11 will be O2j into 1 minus O2j into, we have to take again by chain rule derivative of this with respect to OI1 into WI. Okay. So now you have this term. Now we only have to find this term. So O11 was the output of this layer, sorry, this layer. Summation sigma W1. Here it is W2, I think. Here it will be from I to J. And here you will get sorry, the J is here and it is from the first thing. So here it was Xi W1 Ij plus B2. Here J is 1 because we are talking about the first node. And this is also first layer, first node. So partial derivative with respect to W1 1 this will be O11 into 1 minus O11 into X1. Okay. So what we have to do is just compute the values. We have this value. Here O1 output is this. And the weights and bias, everything is given here. So I have to substitute Xi values, which is just X1 and X2. Wi1 values. W's are given minus 0.5, 1, minus 1. And this bias is given B. I think for this layer there is no bias. This node there is no bias given. On this node there is a bias given. So that bias value you can compute. Then do a sigmoid activation function. You apply on that, you get O11 value. So this derivative is O11 minus 1 minus O11 into the X1 value that you get from here. Similarly, you get this derivative value. These two values you substitute over here, you get this value. This value you substitute over here, and this is this. So there are basically one, and you can do it in this order. First you will want to compute this, then you can compute this, so that will give you this, and here this. Okay, so any doubts in this? If you are asked to compute the derivative of this thick arrow weight, so we call this as W first layer, first input node to the first hidden layer node weight vector, and the squared error loss function is given to us. So to compute that by chain rule, we got this. You take the derivative with respect to first, like your cost function is applied in the like here somewhere to whatever the output was, whatever output OJ you get here, and T you use, apply the cost function on these two. So the cost function is a function of these. You apply a chain rule, you get this into this, or summation over J. This again you can, by chain rule you can split into this, and these can be computed sort of directly. So any doubts? So in practice, like the way these are programmed in like popular deep learning frameworks like PyTorch or TensorFlow, these are, there are many others also, but these are the most popular frameworks which are used to code deep neural networks. There, these computations these computations are done in via directed acyclic graphs. So if you see, like there is like a graphical way in which these computations happen. You go from this to here to here to here, and this also, each, the derivative with respect to this and this to this, that can be computed parallelly, and many of the terms can be reused. When I am computing the derivative for this part, there is some term coming that can be reused for the derivative of this part to this. So that kind of occurs concurrently and parallelly, uh, the way those algorithms are coded in these popular frameworks via parallel programming, and that makes things very faster. I mean, there are like tricks they have used to make it quite faster, and the way they program it depends on what kind of computer architecture, graphic card they have designed and things all like that. Like Nvidia, which is the most popular graphic card provider company, they have their own programming language called CUDA, which is based on C++, on which they write programs for all these computations. But like if you are just a practitioner of deep learning, then you use things like Python, which has libraries called PyTorch and TensorFlow, which internally call these CUDA programs. But we don't have to worry of how these CUDA programs are doing internally. We just use the higher level abstract frameworks where we say like I need this many layer, this much node, this is the cost function, this is my learning rate, and it will automatically run the algorithm and give you optimize the weights by doing gradient descent iteratively, give you the final network. But internally, all these computations happens, and some people have figured out these things. Once they figured out, then people coded it. Then popular libraries started to come up, and then people started using it all over. Okay, that is just some history of these things. Discussion. So let's assume we have a simple function f x y z equal to x plus y into z. We can break this up into equation q equal to x plus y and f of x y z equal to q into z. Using this simplified notation, we can also represent this equation as a computation graph. Yeah, so this is a kind of a graphical directed acyclic graph. Now let's assume that we are evaluating this function at x equal to minus 2, y equal to 5, and z equal to minus 4. My voice is audible, no? Okay. We are evaluating the function at these values. In addition, let the value of upstream gradient of the loss with respect to the function. So there is some loss function L, and del L by del F is given as 1. So I think this is del L by del F. And we want to find del L by del Z, something like that. So they are asking us to solve it symbolically and also evaluate. So if I want to find del L by del Z, I need del F by del L by del F into del L by del Z. Or if I want to find del L by del Q, I need del L by del F into del F by del Q. Here it should be F, sorry. So here they are asking del F by del Q. So del F is Q into Z. So del F by del Q is equal to Z. Del Q by del X. So Q equal to X plus Y. So del Q by del X is 1. Del Q by del Y, that is also 1. Del F by del Z is Q. Del F by del X. So del f by del x will be, can write it as del f by del q into del q by del x. So del f by del q is z, del q by del x is 1. Z into 1 is equal to z. And you can verify it here also, at xz plus yz. So del f by del x would have been z. Similarly, del f by del y will also be sort of the same thing. This will also be z into 1, which is z. So evaluating the z value minus 4, we have to put others is 1 1 1. Q is what, x plus y. X plus y is 3. So here it will be 3. Here it is minus 4 minus 4. This is 1 1. Okay. Any doubts? The simple chain rule, and it has been shown via a graph kind of thing. Like as I was saying in the previous, when we were discussing the previous question, these graphs are like, the graph structure is kind of determined, and that is what runs on the graphic processor. So we have even more an extended graph kind of thing here. Let's perform backpropagation through a single neuron of a neural network with a sigmoid activation. Specifically, we will define the pre-activation Z, which is this W0 X0 W1 X1 plus W2, some bias kind of thing. And we will define the activation value alpha, that is the sigmoid function. The computational graph is given like this. In the graph, we have filled out forward activations on top of the lines. I think after you do this, what value you get, that is given here. 600 plus minus 2 is 4. 400 plus minus 3 is 1. It's not 400, sorry, 4 plus minus 3. Okay. We have filled out the forward action on our line as well as the upstream gradient on the loss respect to our neuron. Use this information to compute the rest of the gradients, labeled with question mark. So this is the upstream one. One second. Ah, okay, this is the upstream one. Del L by del alpha. What is alpha? Okay, sigmoid activation. So del alpha by del x naught. So how are things happening here? You did summation over here. You got some value multiplied by minus 1, you take exponential. So the output you get over here is your z, because it is w naught x naught, w naught into x naught plus w1 into x1 plus w2. Okay, so this summation got here, this plus this, you get z, and this is z into minus 1 to get minus z. Then exponential of minus z is done here, 1 plus exponential of minus z, 1 by that. So here you get finally your alpha. L is a loss function that you compute on your alpha. So del alpha by del x naught, that is this. Del alpha by del x naught, you can first try to find out del alpha by z. Del alpha by del z into del z by del x naught. Okay, the alpha is a function of z. So del alpha by del z is something that we know, that is alpha into 1 minus alpha, because it is sigmoid function, into del z by del x naught. So here we have, now del z by del x naught is what? Z is this, del z by del x naught is w naught into w naught. Okay, and with this alpha you can expand, because alpha is equal to sigma of x naught w naught plus x1 w1 plus w2. So this, if you substitute here, you get in terms of the parameters. Okay, del alpha by del w naught will be del alpha by del z into del z by w naught. So we'll get kind of same terms, but del z by w naught will be x naught, and these are like x naught and x1 are kind of replaceable kind of thing. Here you will have alpha into 1 minus alpha into x1. Here you will have alpha into 1 minus alpha into 1, because w2 coefficient is 1. And now these values can be substituted to get the exact values. Alpha value is 0.73 and x naught w naught all are given here. we're just using the chain rule to find these derivatives. These derivatives can be subsequently used to perform the weight updates like W1 and W2, whatever is here. This is for this basically a single layer perceptor. I hope this is part is clear. Okay, then I'll go to the next question. Consider x in Rn and some upstream gradient vector del L del f, and you want to calculate del L del by del x, where f of x is x naught into x. So x is a vector in Rn. You may assume all values in x are distinct. Note that x naught is the first component in the vector x. So x naught is a scalar. This is a vector, and this multiplied with this is, you can say, that vector x naught into x naught x1 x2 till xn minus 1. This is x naught into x naught into x1, so on till x naught into xn minus 1. This is the vector. What we want to calculate is del L by del x. So that will be del L by del f into del f by del x. So this is given to us, that is what they are saying. Assume this is given and you want to find del f by del x. So this will be some vector, because x is a vector, and by its entries will be del f by del x naught, del f by del x1, so on till del f by del x n minus 1. So if we are to find the derivative of this particular given f with respect to x naught, then what do we get? So you have to take the partial derivative with respect to the first thing. So here it will be, this is x naught square, so it will be 2x naught. This is with respect to x1, so here it will be x naught, and everywhere else also it will be x naught. Right? And there is some mistake in this.
Uh, Pranav,
Yeah,
yeah, I have a query regarding that the last statement where it is mentioned that note that x naught is the first component in vector x.
yeah, yeah, yeah.
So, uh,
So that means this is x naught into x, na? First component into x. That is
yes, okay.
what this function is doing. Okay, I think I understood what mistake I have done. Because f, the output of f is not scalar. The output of f is a
F is
vector.
also a vector. Yes, yes, yes.
Okay. So basically, how I should be looking at it is,
And Pranav, I have just another doubt. Like, it won't make much of a difference because whether it's a row vector or column vector, since there's a single like.
which what are you saying? What is the row vector and what is a column vector?
No, no. What I am saying is the given vector x
Yeah,
with the values x naught, x1 up till x n minus one.
yeah.
So I am multiplying a scalar with the I have we have assumed that it's a column vector.
Okay, okay, okay. Yeah, this is a column vector.
Okay, okay, okay.
So if I write like this, then I have uh, some del f by del xi into, sorry, del L by del F into del L by del F by del Xi. Now this can again be written as, because F has different components, so this can be, this will be a vector and this is also a vector. This is like a dot product between the vectors. Just write this as a dot product between the vectors. So if I take a dot product, it should be something like, let's say some j del L by del Fj into del Fj by del Xi. Okay, so this Fj is the jth entry of this vector, and this is the partial derivative of the jth entry with the xi variable. Okay, so let me rewrite this part. So if I write uh, del fj by del xi, this will be, so this is your f whatever you're getting. If I say this as x0, for x0 this will be 2x naught for j equal to 0, and it will be x1 for j not equal to 0, or xj, right? Because except for x0 there is everywhere there is x1, x1, x2 or xj into x0. While for the other terms, del fj by del xi, I not equal to 0, what you will get is, it is 0 for j equal to 0, or j not equal to I, you can say, and j not equal to 0. What I'm saying, sorry. For j equal to 0 also it will be 0, and for any j which is not equal to I it will be 0. When j is equal to I, it will be x naught. So what is finally your del L by del x naught, let's say? It is del L by del f, some vector which is given to us, into del f by del x naught. Now we need to find out what this vector is. This vector we will get from here. So it is del L by del f dot product with, what is the vector here? Two x naught x1 till xn minus 1. Similarly for all others, I not equal to 0, it is del L by del f into del f by del x naught, sorry xi, and you have a vector here. What are the entries of this vector that you get from this part? It is 0 everywhere. In the ith entry it is x naught, and everywhere else it is 0. Okay. So when you take a dot product, you will get a real value. So finally your del L by del x is a vector with these entries, del L by del x naught, del L by del x1 till del L by del x n minus 1. Okay. Any doubts? Then I'll go to the next question. Mm, Assume we have a two-layer neural network as defined below. So this is the first layer, its activation. Then second layer, then activation, you got some output. Then you have this cross entropy loss. Then uh, sum over all your inputs. This is for the ith entry. Ith. Okay. Xi represents a single input example and is of shape dx into 1. So dx is the number of input nodes you can say of your input layer. Further, yi is a single output label and is a scalar. So your network is like you have d neurons in the input, some hidden neurons depending on the shape of w2, and one output neuron y. There are m no total number of samples in our dataset is m. DA1 nodes in our hidden layer. So here there are DA1 nodes. Here there are DX nodes. So Z1's shape is DA1 into 1. Okay. What are the shapes of W1, B1, W2, B2? So what is the shape of this? And this. And this and this. So if A1 is like A1 is the output vector basically of whatever is coming out of here. You have nodes here. You have scalar output of each node. So the vector that is formed that that has a shape of dA1, and that is formed by multiplying a matrix uh, of certain shape, which is W1 into uh, this xi, which is dx dimensional, and your bias that will be for each of this thing, that will also be dA1 dimensional vector, because that bias weight will be for each of this thing. So it is also, so the dimension of this and this should match z1 and b1, and z1 is just pre-activation of each of this a1. So w1 weight should be, because this is dx into 1, so this should be sort of 1 into
DA.
dA1.
Yeah.
So w1 shape is 1 into dA1. b1 is, so this is dA1 into 1 sort of, this is dA1 into 1, so b1 is dA1 into into 1. Oh, what did I write? Sorry. This should be dA1 into dx, right? Yeah. This is dA1 into dx, W1. dA1 to dx into 1 will give you dA1 into 1. Yeah. Is it clear? When you multiply W1 and x, you should get a dA1 into 1 vector. So W1,
Yeah, Pranav, that one, it's the same matrix multiplication rule.
yeah.
M cross n multiplied by n cross p, then it would be m cross p.
Yes. M cross n
Yes,
into
yes, yes, yes.
this vector. When you multiply it by m
N
cross
cross
p,
p. Yeah.
the resultant will be m cross p.
M cross p. Correct.
Similarly, W2, if you apply the same thing, you have dA1 inputs. So I think it should be 1 into dA1, and your output is 1 cross 1. So you'll have just one bias. So it is 1 cross 1, because output is a single output. So Z2 is just 1 cross 1. So if you were vectorizing this network across multiple examples, what should be the shapes of the weights and biases be instead? So weights and bias shape will be still the same, right? Because for all the inputs, we are going to use the same weight and bias matrix. The entries will be updated, but the matrix shape and size will be same. If we are vectorized across multiple examples, what should be the shapes of x and y? So x and y will be, you have m samples. X will be an m cross dx. You can say matrix. And this y can be some m cross 1 matrix. For m samples, each sample you have one output, and for each sample you have a dx dimensional feature input vector xi. What is del j del yi? So this is j. So del j del yi. Sorry, del j. That you can write as is just for the ith sample, right? So that you can write as del j by del li do del li by del yi. For all the other I not equal to, for j not equal to I, it will be 0, the partial derivative. So we consider only the ith terms. Now del I li by del yi, that you need to compute. that you'll get over from here. And for cross entropy, I think I just directly use a formula. Hmm, wait a sec. Formula is y by y hat I minus 1 minus yi upon 1 minus y hat I. Is it something like this?
Y hat I guess it should be in the numerator. Y hat I. Y. Uh,
Y hat I should be in the numerator.
yeah, I
Y hat is
think.
the output of this after activation. So I think it's in the denominator.
Okay. Yeah, let me check that.
Because this one log of delta of partial derivative of yi with respect to log will be 1 by log y hat I. So you will get like this. Okay. Now what is del j by del y hat? So what did I compute here? Del j by del li into del. So this del j by del li will be what 1 minus 1 by m, right? So minus 1 by m into this. Now we also need to compute del j by del y hat. So if you compute from here, what you'll get is no, this is y hat only. That will be a vector basically. For each I, you will have a different, what to say, this thing. With this item is not here. So this will be m dimensional vector with this as the entry corresponding to I. What is del y hat I del z2? So this they want to call it as delta 1 I del y hat I is this del z2. So y hat I is sigma of z2. So del y hat I by del z2 will be sigma of z2 into 1 minus sigma of z2, because we can assume it is sigmoid. Sigma is sigmoid. It's not written here, but we can just assume sigma because here they have written ReLU. Sigma must be the sigmoid function. So I think this is all what is asked in this part. This they are calling delta 2. I think in the next page there is continuation of this. Any doubts still here?
Yeah, Pranav, can you repeat the last one that del y by del z2, that one?
So y hat I, so I is the superscript actually. Sorry. This is sigmoid function over z2. So when you are taking partial derivative of sigmoid function, it will
The
be
sigma 1 minus sigma, yeah.
yeah. So that only bracket.
Okay, okay, okay.
So from these two parts we got some terms. Maybe they are used in the next part. So I'll go to that part. And there is no question in this part. Okay. So the same setup. Note that so 4, 5, 6. Note that xi represents a single input example and is of shape dx into same things. What is del z2 by del a1? Del z2 by del a1 will be this weight matrix, right? Because z2 is a vector. Z2 is a vector of shape. What is it? Oh, it's a 1 cross 1 only, no? Okay, Z2 is 1 cross 1.
Z2 is 1 cross 1, yes.
So it's not. This is not a vector then. A1 is a vector. A1 is a vector of dA1 cross 1, I think. So del Z2 by del A1 will be a vector of del Z2 by del A1's first entry till A1 dA1 entry. So that will be basically, so W2 is of shape 1 into dA1. So it will be this W2 vectors first entry, W2 vectors second entry till W2 vectors dA1 entry. That will be your partial derivative for this. What is a1 del z1? A1 is ReLU of z1. So ReLU function is what? It is equal to 0 if z is less than 0 is equal to z z we can say greater than 0.
Greater than equal to 0.
So if we are writing like this, then what is this? Now z1 is a vector. Yeah, z1 is a vector and a1 is also a vector. They are both of the same size, of shape dA1 cross 1. So if I were to compute the partial derivative of its jth entry with some ith entry where j and I are not equal, then that entry will be 0. If j not equal to I, because a1 j is just a function of ReLU of z1 j. It's not, z1 I is not a part of it. So derivative with respect to z1 I will be 0. Now if I am saying del a1 j with respect to del z1 j, then that will be 0 if z1 j is less than 0. So here actually I should have written z1 j if z1 j greater than 0. z1 j, separate this part. z1 j greater than 0. And this is 0 if z1 j greater than 0, and this will be 1 if z1 j greater than equal to 0. So what we will have is this partial derivative will be a matrix where all the diagonal entries will have 0 or 1 depending on the value of z1j, and all other entries will be 0, non-diagonal entries. What is del z1 by del w1? Del z1 into del w1. So z1 is this. z1 is a vector of shape dA1 cross 1, and w1 is a vector of shape dx cross 1. So again we will have some del z1 I del x. Okay, let's forget about that superscript I and write here j. Oh sorry, I wanted w. W1. Now w1, if you recall, it was actually a 2D matrix. So we'll have to, let's say if it's jth uh, jth column, I guess that will be a vector. What will be the entries of this vector? It will be the entries of x1, x2 till x dx, right? This is what you'll get. So j is the row, I guess. J is the row. Da1th row. J is the row. With respect to each row, you will get one vector. So all in all, this del z 1 I by del w 1 will be a matrix. Where each row is x1, x2, x dx, x1, x2, x dx, and so on. And if I have dropped this I subscript also, then it will be a 3D matrix that I can't write. So what will be the shape of delta phi I? It will be I think it can be tricky because we must have followed one convention throughout. But let's just assume for now it is z1 is da1 cross da1 cross dx. I think this is the shape. This is da1 cross dx now. Okay, so maybe a better way to write will be, so what we can say is if j is not equal to I, then those entries will be 0. Only when j is equal to I do I get this. Yeah. So what you will have is 0 throughout, and the ith thing will be x1, x2 till x dx. and then every else 0. Ith column. So del J by del W1 is what finally? So I can do del J by del Y into del Y by del Z2 into del Z2 into del A1. So it is basically the multiplication of everything that we have computed till this point. Del del 1I into del 2I into del 3I into del 4I into del 5I. It will be something like this, but we will have to take care of how the shapes are. I think in the last one I have made some error. I have a strong feeling I have made some error in the last part regarding the shape. But if we have these values, then we can know. And for this, because W1 is a matrix, so with respect to each entry, so finally you should get a matrix. So J is a scalar, the cos that you get from here. W1 is a matrix. So with respect to each entry, you will get. So this will be a matrix with del J, W1, Ij, or W1, 1, 1, W. Sorry, I should write it. Del J, del W1, 1, 1, del J, del W1, 1, 2. This is 1 comma 1 comma something like that. Comma. This is DA1, I think. Similarly here, del J, del W1 comma DX comma 1, and this will be del J and del W1 comma DX comma DA1, something like that. And this will be your final up matrix. Okay, here DA1 rows, but here I think I wrote DX rows, so it will be transpose of this. Yeah. So that way you can adjust and just see how things are going. But roughly this is the idea. I hope you understood. Any doubts? So if you have like any particular doubt you want to ask, or if you want me to discuss in the class, then you can mail me also. And just write my mail in the chat. You can mail your doubts and I can discuss that in the next session. Otherwise, I'll just end the session. We're out of time.